Hello. So we are the EigenBot team. I'm Logan. There's Edward, Henry, and of course Lou. So we will be presenting some updates on our EigenBot neural distributed control.
All right, so you may have seen it in the lab, but the EigenBot, to give a brief introduction, is a modular system composed of reusable embedded segments that we call modules. And so you can kind of see here that Julian is hot swapping some general modules on our EigenBot in a hexapod configuration. And so that's a special thing is that you can take it apart and basically add specialized end effectors and get a totally different functionality. And so part of the modularity goes within the module with the eigenbrain, which is operated on PSOC. And so as you can see with the diagrams on the bottom, there is a module with the eigenbrain inside of it, and there's some contact pads that allow the module to sense the orientation of nearby modules, the direct neighbor. And because of this, we can use some special software to configure into multiple deployments, as you can see in the far right. Next slide, please. Yeah, so the secret behind our modularity with this robot is called EigenBus, and essentially it is a firmware protocol designed for intermodule communication. The messages that it sends between the nodes is a hex decodable simple message, and the software also has a automatic topology generating feature where it can generate a tree and show the nodes in a upstream and downstream fashion. And so you can see here that the computer/root node is the most upstream node, and it communicates duplex using full duplex using RS-485 serial to the downstream nodes below that also have their own processing units. Next slide, please. So a lot of our inspiration comes from insects because of the distributed computing functionality, we can now kind of imitate different insects. So we have here is the anatomic analogy between a couple of legs and the actually a couple of joints in one leg, and our EigenBot analogy. We have three joints here and then some neural pools and muscle groups that Logan will be talking about.
So a bit of background in stick insect controller. The legs are consist of neuron pools of motor neurons, which drives the muscles, and also interneurons, which acts like a feedback controller that transforms the feedback signals to influence two main elements. Uh, the motor neurons, just mentioned before, and also the essential pattern generator unit, or CPG in short. So the CPG drives the insects to stance and swing phase and is present on each joint on the insect's leg, acting independently and modulated by proprioceptive feedbacks. And they have no direct connection between them. And also in between the limbs, there are six behavioral rules called the Crouzet's rules that dictates the influences between the limbs. So these rules either inhibits or excites swing or stance phase, uh, and this ensures the convergence of the gates into emergent behaviors, producing gates between among waves, tetrapod, and also tripod gate. So this is what we want to achieve on EigenBot with our neural controller. So this is our control architecture for one leg. So with CPG running on each joint and connections to different sensory feedbacks, which are mainly joint load, joint position, and velocity. So each sensory signal can have excitatory or inhibitory effects that increases or decreases the activity for each CPG units or motor neuron units respectively. In which case, the CPG units are the ones that contributes to timing between stance and swing phase, and the motor neurons contributes to magnetic control of the joint. Here, we do not explicitly model the motor neurons, but rather rely on a separate control layer of the PI controller on each dynamic cell, which drives our joints on the EigenBot. So this mirrors the stick insect's joint controller that converges to a set velocity as fast as possible, which reduces the moment produced due to different velocities in each foot. And additionally, we're also implementing the interlinear rules as mentioned before. Instead of 6, we have implemented 3 in total. So now we present our simulation results. We also have hardware results, which we'll talk about in a bit. So right now, the robot is walking on flat ground, and the robot usually converges to stable gait, as seen in this video, within 1 or 2 steps with our controller. In this video, it converges with 1 step only. And then we have block obstacles. We created a few block obstacle environments. This one, on the right, we have our neural controller. As you can see, the robot is traversing through the blocks relatively easily, and the one on the left is the tripod gate that we have on by default on the EigenBot, which is predefined. So this is a second case. One thing to note here is we have put a third block on top of the second block, creating a slope, and this is also not bolted to the ground, meaning it could wobble and thus unstable for the robot. But as you can see, our robot is able to adapt to this wobbling motion. And once it has stepped down, it is able to converge back into its tripod gate, which is quite stable. So, and then we move on to terrain. So in this case, the robot is required to constantly be walking on a slope and also traversing through uneven surfaces. And again, the neural controller is able to climb up and down the hill fairly easily, while the predefined gate has some trouble to traverse through the terrain. And you're muted.
Yeah, and we also implemented curve walking / steering. This is done by reversing the motion of one middle leg, and the other legs are able to adapt to the sudden change of the middle leg very quickly and continuously walking after steering right away.
We also works extensively on the firmware implementation on our modular platform. So we created a firmware structure that shares information for local feedbacks within a limb and also between limbs, with independent controller running on each joint, and with no explicit coordination and phase offsets between joints and between legs. So our hardware results is still quite preliminary. We tested 1 leg and then 2 legs for interlimb coordination. Here we have 4 legs. We didn't tune explicitly for our 4-leg controller, but rather use whatever we had for 6 legs and applied it on 4 legs. And it is able to create some alternating gates between the 2 pairs, which are diagonally, almost diagonally in phase. So one thing to note here is that the elbow sometimes touches the ground, and this is because of the inherent difference between the robot and also the insect, where the insect doesn't need to consider such dynamical movements because it's very light and doesn't need to worry about its weight. And nor does it have a sense of balance organs for most cases to catch the fall. We do have an IMU unit on each eigenbrain, so a potential future step is for the controller to be able to have a reflex that catches its fall with the front limbs or the hind limbs when there is a large acceleration on certain axes. We also worked with 6 legs. So in this case, we have it converges into a relatively slow gate. The behavior is not ideal yet due to weight tuning issues and also symmetry differences. One thing to note here, though, is that the middle leg is striding almost in phase, which we do observe in simulation when there's a large force needed. For example, when there's a bigger slope, and the controller will converge to a almost in phase middle leg, so that it will propel it upward a bit harder. But obviously, this is not ideal for flat terrains. So we will keep working on this so that we can achieve a more robust controller in real life, as we have demonstrated in the simulation. Yeah, so that's our presentation. We are still working on getting the quantitative results. We're thinking of using a few different stability criteria as well. And we're open to any questions.